Hello students, welcome back. Let's go to problem 3. Mathematically speaking, problem 3 is nothing but a repetition of problem 1. Different setting, different numbers, different types of drugs, but it's basically talking about the same type of mathematics. Two-sample inference with proportions. Okay, let's begin. The article, Remdesivir in adults with severe COVID-19, a randomized, double-blind, placebo-controlled, multi-center trial. Published at Lancet, volume 395, pages from 1569 to 1578, May 16, 2020. So remdesivir is a medicine originally made for an Ebola medicine, and we are using it for, these people are using it for COVID-19 medicine, and this is a result. 237 patients were enrolled and randomly assigned to a treatment group, those who received medicine, or a control group, those who received fake medicine, placebo. 158 to treatment group with remdesivir, and 79 people to placebo group. Do they add up to 237? 158 plus 79, 237, yes, that's right. One patient in the placebo group who withdrew after randomization was not included in the ITT population. So this 237 does not include this one person. All you have to do is 158 and 79. This sentence over here, I just copied it because it was part of the analysis here in this medical paper. This one has absolutely nothing to do with mathematics. It is there to certify the validity of this medical experiment, not the mathematics. The mathematical analysis are all about 158 versus 79. Now those are sample numbers, sample sizes. So N1 is 158, N2 is 79. That's what we have so far. And the color coding will help you. And then our trial found that intravenous remdesivir did not significantly improve the time to clinical improvement, mortality, or time to clearance of virus in patients with serious COVID-19 compared with placebo. Basically, it's a failure. Not a failure of experiment, Medical experiment itself found out something, so that's not a failure, but the failure I mean by the use of remdesivir, Ebola medicine, in COVID did not turn out to be so fruitful. The result of the study includes 28-day mortality rates of 13.9 for remdesivir, and 12.8% for control group. So what we have, mortality rate is higher for the people who received medicine versus those who received placebo, which contains nothing but just salt water. So as far as statistical analysis is concerned, this part is totally unnecessary. Let's go to the next piece of information. 28-day clinical improvement rate of 65.2% for remdesivir group versus 57.7% for the control group. This part makes some sense because improvement rate is higher for those who received medicine versus those who did not receive medicine. So this part, second part may need some statistical analysis, which we will start shortly. But the first part does not need anything. I included all these numbers. Well, I included all these numbers because when you actually have to do some statistical analysis for other discipline, you get all those numbers and then you have to make sure which is which and take appropriate numbers. And for that purpose, I left this part. So just like this sentence over here, it doesn't do anything. The second part, that's what we are interested in. So let's talk about that second part. P1 is about 65.2. %57.7%. I forgot the decimal. Blue, red. As a matter of fact, these cannot be quantities. Nothing is precise in statistics, so I need this approximation symbol. Using these, can you find the standard error? Square root of SC1 squared plus SC2. Can you find it out? What is SC1? P 1 minus P over N, isn't it? But that is for the first group. So I need P1 here, P1 here, and N1 here. Likewise, SC2 is equal to square root of P2, 1 minus P2 over N2. So that is for treatment group who received remdesivir, and this is for control group who did not receive the medicine or placebo, the fake medicine. We have all these numbers, and then we have the formulae, this and that. So finding out the standard error for this two-sample inference, I'm going to stop here and I'll leave you to it. Okay, next. Find a 95% confidence interval of the difference in the percentage point. Okay, the difference is, let's see, 65.2% versus 57.7%, isn't it? So it is 0.652, excuse me, minus 0.577. So the observed difference is 0.075 or 7.5% difference. So you'll have to get appropriate normal figure around this difference, 7.5% point. Let me show you just a little bit more. So 95% confidence interval, 95% in the middle, 2.5% here, 2.5% there, and the observed difference here is 0.075 or 7.5% point difference. Using the SE you found out in part A, you'll have to find out this endpoint x1 and that endpoint x2. Good luck. I'll stop here. Oh, never mind, just one more. Z-score is end minus center over SC, isn't it? And that's basically what you're looking for. You want to find out this endpoint here using this formula, Z equals to n minus center over SE. And the center, of course, this is 7.5% point difference, 0.075. And SE you calculated before, you're looking for end. And then Z-score is something you'll have to figure out from this situation. I'll stop here. Okay, that concludes hints on problem 3. And let's go to problem 4. Okay, here we go. Clearly, the study discussed in the previous problem suggested that remdesivir is not effective reducing the 28-day mortality rate. Actually, the mortality rate increased. It doesn't mean the drug is actually killing people. It's far more likely that it really did nothing or close to nothing, so that it's just a randomness you're looking at. Random error. Now, how about 28-day clinical improvement? 65.2% versus 57.7%. The difference, the observed difference was 7.5% point or 0.075. Is that enough? That's the question. Now, how do you set up hypotheses? Two-sample inference, what's the null? Difference is equal to what? 7.5% point? No. Difference is equal to 0. The 7.5% point we saw before, 0.075, that appears for hypothesis testing, especially when you have to use that critical value or p-value. Next, greater than 0 or less than 0. Pretend you didn't see this. Okay, there are two things. Number one, do you want clinical improvement rates to be higher for this medicine? More improvement or not? You want more improvement, right? Clinical improvement so that they can discharge it early. So we want something positive. And that's why we want the difference is greater than 0 or significantly greater than 0. Another way, the difference you calculated was 0.075, and that's positive, so that's another indication that you'll have to take greater than 0. All right, so much for hypothesis setup. Next, the testing, and we have 4 different methods. Here, I'm going to explain those in 2 different methods. Critical value method number 1 and probability value method number 2, but I'll do those in separate videos, not here.